Hi, my name is Alexis Wingbach, and this is my public lecture review of the Surprising Expansion History of the Universe by Adam Riess. So basically, it was about how Adam Riess and his team made the Nobel Prize-winning discovery that the universe may actually be accelerating as it expands instead of decelerating, which is a pretty big jump from what we originally thought. So first, we have to go about how are they measuring distance, velocity, acceleration in space, and obviously they need distance to do that. And they use these things called standard candles, which are supernovas of known luminosity that we can use that luminosity to measure how far they are from us using the inverse square law, which is pretty cool. And so using this, we take type 1a supernovas, which are made from white dwarfs, which are 1.4 times the mass of the sun, and we take those and basically we use their luminosity to discover this. They're like the standard. And so basically what he did, what we've done in the past, is Hubble in the early 20th century, he used standard candles to make a graph of velocity over time. And so he did the change in distance over time to time. And so the slope of this was called Hubble's constant, and that would have been the expansion rate of the universe. When he originally did it, he got that using that expansion rate constant, he learned that the Earth was probably going to be around 2 billion years old, which we knew wasn't right because we knew the Earth by then had to have been at least more than that, like a couple billion. So that obviously wasn't right for the whole universe. And so we've worked a lot at it since then because we need to know a lot about the physics of galactic bodies in order to determine velocity. And so it's also important to note that we are using this constant to determine like the mass of the universe, and then we can use the mass to determine like the age. And basically, if the universe is really heavy, what's going to happen is we assumed it would decelerate really quickly like that, and there would be a big crunch and it would collapse. And so if it was a light universe, it was going to decelerate more slowly, and it was just going to kind of like straighten out. So Einstein's time, they believed that like the universe was pretty static, that it wasn't expanding, but that didn't make sense because with attractive energy, so we created repulsive energy, which is basically like dark energy, meaning that it kind of repels and it would kind of create an unsteady system, which would mean the universe is going to expand or shrink and would eventually collapse. But yeah. So again, Adam Riess, it's 1995, and he, for his thesis, assembles a team, and he gets a lot of data from a bunch of 1A supernovas, or actually just white dwarfs, and tries to find supernovas in order to use them. So you might be thinking, well, these would all be from the same time, right? So how would we use that to measure the change over time? Well, fun fact, if an object is far away enough, that means that the information from like a long time ago might not have reached Earth yet. Those light waves are still traveling. So we can actually find those light waves and measure them and find what the supernova looked like luminosity wise way back in time, which is pretty cool. It's like a snapshot from the past. And so by using a bunch of photos taken by spacecraft devices, Riess assembled a computer program to go through and flag images with high luminosity, like they were supernovas and not just white dwarfs anymore. And he used all those images to to measure the luminosities and add on to Hubble's graph of velocity over time. And so when his computer program did all this and it went to measure, like calculate the mass using the Hubble's constant it got a negative number, which doesn't make sense if the universe is expanding at a slow rate. Like, as it slowed down, if it's negative, then that means it must be accelerating. And so met with his team, he was like, whoa, it's accelerating, that's crazy. And so they eventually published that information, and it actually won a Nobel Prize. Another team also published the similar results a little bit after that, so they kind of were on the same page. And so, like, why do we think this is happening? We don't really know. We know that it might be dark energy, which is like a repulsive energy. The energy theory Einstein came up with might not be right, or there may be some other kind of energy filling the vacuum of space, causing it to accelerate. And so I was like, wow, this is pretty cool after the presentation, but I was surprised to learn that it happened 25 years ago is when they won this. So I was like, what's happened since then? Is this true? Is this false? So I did a little bit of follow-up, and I learned that we've actually found data to support the fact that the universe is accelerating, ever expanding at an accelerating rate, and we found that in baryon oscillation waves. So basically, when the universe was formed, there was a lot of hot plasma, and pressure waves went through this hot plasma, and when the plasma sort of flash froze as the universe got cooler, it trapped the pressure waves within it, and we can use those as a standard ruler, or something of known distance, known measurement. And so we can determine where galaxies are on it over time using like redshift. We can see how they're moving, and using those clusters, we found that it does look like they're getting further apart, meaning the universe is accelerating. So this theory is still continuing to be proven. It's not 100%, and we still don't know a lot about how it's working, but I really enjoyed it, and I hope you did too.